All right, hello there, differential equations, day number 9. We're going to solve differential equations using Maclaurin series. So let's get into a couple examples. Let's go. Okay, so example A has a couple parts here. We're gonna dive into this. Let's do it. Example A says, approximate the particular solution to the differential equation below using the first 4 terms of a Maclaurin series. So before we get into that, let's talk about the Maclaurin series. So a function y is going to be approximately equivalent to y at 0 plus y prime at 0 times x plus y double prime at 0, x squared over 2 factorial, and so on and so forth. I'll go out to the third derivative of x cubed over 3 factorial. So this will approximate a function, right, based on dy dx, and the second derivative and the third derivative, etc. So I can think of course, I know y of 0. I've got that right here. It's 1. So I've got that first term. Y prime at 0 is going to be equivalent to dy dx located at the point 0, 1. Okay, and then y double prime at 0 will be equivalent to the derivative of the derivative, dy dx. So dy, or d squared y dx squared, also evaluated at 0, 1. And likewise, we can see that the third derivative would be useful in the same way. So provided none of these are 0, right, we could rely on these 3 outputs to help us to build the first 4 terms of the Maclaurin series. Now we might have to go out to the 4th derivative if one of those coefficients is 0, but I guess we'll find out. Okay, so let's do a quick derivative work on this. So I know y at 0 is 1. Let's find dy dx at 0, 1. All right, so I'm going to plug in a 1 for y, and it's not dependent at all on x. So dy dx at 0, 1 will be 3. I know this value right here will be 3. I know this value here is 1. Let's look and see the second derivative. Now, in order to get the second derivative, what I'm going to want to do is take the derivative of dy dx, both sides of that equation, and that's going to yield us a little chain rule work. The left side will be d squared y dx squared. The right side, using the chain rule, the derivative of y squared is 2 times y times dy dx. Okay, it's implicit in its manner, and the derivative of 2 is 0. Therefore, there's the second derivative. While I'm at it, I'm just going to do the third derivative, and then we'll do some work with evaluating each of these. So I'm going to take the derivative with respect to x to the second derivative. That'll be like taking the derivative of 2 times y times dy dx, which is going to require both the chain rule and the product rule. This will yield for me the third derivative. Thank goodness I only have to do this here, and I'll give it up right now, but all of these values will be non-zero numbers. So product rule on this would be give me the derivative of 2y is 2 dy dx, and I'm going to leave that second dy dx alone, plus I'm going to leave 2y alone and multiply it by the derivative of dy dx, which is the second derivative of our function. Okay, so here I've got my second derivative, and here I've got my third derivative. So let's do some algebra here, and let's find the second derivative located at 0, 1. All right, so I'm going to do that work here, and then I'm going to put the answer right over there. Okay, so that'd be 2 times y, so the second derivative evaluated at 0, 1 is going to be 2 times y. Well, y at 0 is 1, times dy dx at 0, 1, which is 3. So that'll equal 6. So I get 6 there. And the third derivative, evaluated at 0, 1, is going to be equal to 2 times dy dx, which I knew was 3, times dy dx again, which was 3, plus 2 times y, which was 1, times the second derivative, which was 6. Looks like, if I'm not mistaken, that'll come out to be 30. So I can say confidently that y, our solution to the differential equation, will be approximately 1 plus 3x plus 6x squared over 2 factorial plus, what would that be, 30x cubed over 3 factorial. If I wanted to simplify that, I actually could quite nicely. That would be 1 plus 3x plus 3x squared plus 5x cubed. And right there, in either of those two forms, would be an approximation in polynomial form of the solution to the differential equation. Okay, so let's now look at part B. I guess, whatever, the second part of part A. Using Euler's method with 2 equal steps, determine an approximation for y of 1. Okay, now I'm not going to use my polynomial. I'm going to use dy dx, right? Because in Euler's method, we use a given point. And here I was nice to you. I said only 2 steps of equal length. I'm going to take dy dx, which is given, times delta x plus y sub n, and that'll give me my next y value. All right, so I'm starting at the point 0, 1. Okay, so dy dx at 0, 1 I was given up above was 3. Now my step length is going to be a half. All right, I'm going to add that to 1, and that's going to give me, what would that be, 5 halves, or 2.5. Okay, so that would mean that my ordered pair for my second point that I'm going to utilize in just a moment would be 1/2 comma 5 halves, which is equivalent to 2.5. Okay, so after I do this again, this should yield me an approximation for y of 1. Okay, so let's do it. So dy dx at 1/2, oops, dy dx at the point 1/2 5 halves. Oh boy, let's look at that. dy dx at the point 1/2 5 halves is going to equal 5 halves squared plus, I'm going to write this as 2 as 4 halves. Actually, sorry, I'm going to write that as 8/4. You'll see why in a second here. Okay, so 5 halves squared is 25/4 plus 8/4, which is going to equal 33/4. Okay, so 33/4 is dy dx located at x equals 1/2 and y equals 5 halves. I'm going to multiply that yet again by 1/2, and I'm going to add it to, and actually I'm going to write this, instead of as 5 halves, I'm anticipating eighths. So I'm going to have this as 20 eighths. Okay, so 33 eighths plus 20 eighths is 53 eighths. Okay, so I'm saying that y of 1, is approximately 53 eighths. Now you could do, I don't know what that would be as a decimal to 3 sig or whatever. But let's see, 48 So I think that would be 6.625, I think. Hang tight. Let me get my calculator. Wow, how come I can't divide numbers? Okay, so 53 divided by 8. Hey, I was right. 6.625. So 3 sig figs, I don't know if they'd have you answer this question this way, but 3 sig figs would go 6.63. Now, will this be an overestimate or an underestimate? Well, over and underestimate has to do with concavity, right? And concavity has to do with the second derivative. And the second derivative at the point at which we are working, right, is positive. It's 6, right? You can see it way up here. Therefore, let me clean this up, move this down a little bit. Since the second derivative at the point 0,1 is greater than 0, aka it is 6, then 53/8 y of 1, which we had was 53/8, right? When the function is concave up, your estimate will be an underestimate is an underestimate. Hey, there you have it. That's pretty cool. All right, let's try one more example. All right, use a Maclaurin series to show that the solution of the initial value problem is y equals tan x. Okay, so we're supposed to show that this is true. All right, so I'm going to build a Maclaurin series, no different than I did before. All right, so y, our function, is going to be approximately equal to y at 0 plus y prime at 0 times x plus y double prime at 0, x squared over 2 factorial, plus, and we're going to go, I don't know, we'll go out to that third degree term yet again, just to be safe, so we can see a pattern. Okay, so we know y at 0. Y at 0 is 0. Okay, let's find y prime at 0. Well, we're given y prime, right, it's y squared plus 1. So because I know that y of 0 is 0, then I'm going to take 0 squared plus 1. Okay, now is when it gets a little bit more interesting. So I'm going to have a 1 here. Now it gets more interesting because, of course, I got to determine y double prime. So y double prime is going to be equal to the derivative with respect to x of y prime, which was y squared plus 1. So y double prime will equal 2y times y prime, and the 1 drops off. So y double prime at 0 is going to be equal to 2 times 0 times y prime at 0, which was 1. Okay, so we're going to see that y double prime at 0 is equal to 0. Okay, so far 2 of our terms here are 0. That's great. We see that we will have a linear term since y prime at 0 is 1. Let's find the third derivative. Okay, so let's work that. I'm going to choose to use, let's go purple. Okay, so let's find y triple prime and then y triple prime at 0. So y triple prime will be equal to the derivative of y double prime with respect to x. All right, so I'm going to take the derivative of this, right, with respect to x. So y triple prime will equal, and of course, I'll use the product rule here. So this would be 2y prime times y prime plus 2y times y double prime. Interesting. Okay, so y triple prime will be equal to 2y prime squared plus 2y times y double prime. All right, so y triple prime at 0 will be equal to 2 times y prime at 0. Well, y prime at 0 was 0. Okay, so y prime at 0, oops, I'm sorry, y prime at 0 was 1. Okay, cool. So we're going to take 1 and square it. Plus 2 times y, well, y at 0 was 0. I can see it up here in red. So it won't really matter, but y double prime at 0 also in green right here is 0. So it looks like y triple prime at 0 will be equal to 2. All right, so let's build this polynomial. I see that I get 0 plus 1 times x plus, it looks like then my second derivative, which would be 0. I'm just writing out all the terms, even though I don't need all of them, because they will reduce, some of them at least. Plus y triple prime, which is 2 x cubed over 3 factorial. Okay, so we can say that y is approximately equal to x plus x cubed over 3. Leave the rest to the imagination, even though I have an idea of what it's going to be. So let's build the polynomial for tan x and show that these two are equivalent. Okay, so let's say that y equals tan x. Then y prime would equal secant squared x. Thus, y double prime will utilize the chain rule, which would be 2 secant x, and then we'd multiply by the derivative of secant x, which is secant x tangent x. Okay, now y triple prime will equal the derivative of that. Now, before I create that, right, I'm going to compact this a little bit and call the second derivative. Let me back this up a step here. I'm going to rewrite the second derivative as 2 secant squared x tangent x. Okay, so I'm going to use the product rule and the chain rule to find the third derivative. Okay, so the derivative of 2 secant squared x is going to be very similar to the second derivative itself, but that'll be 4 secant x times secant x tangent x. So that is the derivative of 2 secant squared x. I leave the second alone, which will be tan x. Now I'm going to add the derivative of the second times 2 secant squared x. So I leave the first alone, and now I'm going to multiply by the derivative of tan x, which is, of course, secant squared. So there is y triple prime. Let's rewrite it, clean it up a little bit. That's going to be 4 secant squared x tangent squared x plus 2 secant to the 4th x. Okay, so now let's build the polynomial in the same way. Well, y of 0 equals 0 because the tangent of 0 is 0. Y prime at 0 is going to equal 1 squared, which, oh, by the way, is also 1. Y double prime at 0, which I didn't label accurately, that should be a double prime. Y double prime at 0 is going to equal 2 times 1 squared times 0, which is tangent at 0. So that'll equal 0. Go look at that. Very good. And y triple prime at 0 will equal 4 times 1 squared times 0 squared plus 2 times 1 to the 4th, which will end up being 2. Now, we're not going to prove that the remaining portions of the terms are all equivalent, but you can see here that it looks promising. Alright guys, that's how you use the Maclaurin series to find solutions to differential equations. See you in the next video.